remember, so in general, all chemical reactions have reactants. Okay, but not necessarily products. So the only way you can get a product if the product is more stable than what you start with. So So again, all chemical reactions have reactants. That doesn't necessarily mean they have a product. Okay. Kind of like the whole thing, the stability. If the products are not more stable than the reactants, why would the reactants want to do that? Bring it next week. Did you have a case for it? Don't leave it in a hot car either. No, bring it inside. Okay, now a lot goes on in chemical reaction. One, it just doesn't happen. Chemical reactions have to be started. And just like we have a match, the match doesn't spontaneously burst into flame. You've got to provide a spark, whether you scratch it on something or take a flame to it or something. You've got to give it some energy, otherwise it doesn't happen. So the bonds have to break. That's why you have to supply energy. So the bonds won't break unless you supply energy. Now, if your reactants are super unstable, we were just talking about this in my other class. If you've got something called, for example, an acid chloride, very unstable. It doesn't need much to get moving because everything is more stable than a particular acid chloride. But normally you've got to supply energy to break the bonds. Okay, so then bonds reform. Bonds break, they reform. And the reformation process usually is more stable than that you started with. But if the bonds reform are what you start with, because bonds can go either way. The bonds can break. When they reform, they can make the reactants all over again, or they can make the products. And there's a ratio between the two. That ratio is called equilibrium constant.
that you're gonna talk a lot about in one B. The end of one A. But there's always a ratio between the two. It's never all one. It may seem like it's all one, but it's usually not entirely all. Could be a 99.99 to 1 ratio or a 1-to-1 ratio. But the point is, when the bonds break, they have the option of reforming what you started with or going on to products. Now, let's look at some graphs. Okay, so we have reactants, bonds are breaking, products, bonds are forming. So this is a two-way street. In the middle is where everything is broken apart. A fancy name for that is called the activated complex. So that's right here. It's just a bunch of taken apart atoms ready to be put back together. Now, that's an unstable place, the activated complex. That's why it wants to reform something. And it's going to fall back to reform reactants. That where it's going to fall down to form products. Now, this is a graph of potential energy. The higher the potential energy, the more unstable things are. So if you can lower the potential energy, it can become more stable. That's why activated complex, notice, has a really high potential energy. So what does it want to do? It wants to become lower potential energy. It does it two ways. It reforms the reactants or forms products. Now, if the products are lower in potential energy than reactants, like here, then the products are favored. Products are higher potential energy, like here, they aren't as favored as much, if at all. So the energy required to break the bonds of the reactants is called the activation energy. And that's this energy here. And usually it's in the form of kinetic energy. So kinetic and potential energy can be interchanged back and forth. So what we're doing is we're converting kinetic energy here into potential energy, raising potential energy of those atoms. The point of being unstable and want to do something, become more reactants or become more products. Okay, so the activation energy is that spark. Whether it's a strike of the match or lighting the little kindling to get your fire going, that's the activation energy. Gets it up to the activated complex, and that breaks down into reactants and products. Okay? Now, if the products are more stable than the reactants, the potential energy difference between those two is converted into kinetic energy. So this difference is converted to kinetic energy, which is built as heat. So when the products are more stable than the reactants, the reaction gets hot. If the products are more or if the reactants are more stable than the products, the reaction gets cold. So if it gets hot, it's called exothermic. Exo meaning thermic energy is leaving the reaction. And if you're holding it in your hand, it'll get hot. Endothermic means the reaction requires energy. So it pulls it from your hand if you're holding it again, and you feel coldness. Because your hand is losing kinetic energy. And remember, temperature is a metric to measure kinetic energy of the molecule, movement of the molecule. All right, so you need to know the difference between exothermic and endothermic. Know what that means. Activation energy, just basically the parts of this graph. Where's the activated complex? Why is it the most unstable point of the reaction? Because it's the highest potential energy. Why do some reactions have no product? How would you answer that? Go down to the second graph. That is so much higher potential energy reactants, it'd be hard for it to happen. Hard to overcome that potential energy difference between the reactants and products. Now, there's some underlying things that can motivate that, because you can have a cold pack. There's a little glass ampule in a cold pack. In fact, in Chem 1A, you actually make a cold pack and a heat pack in lab. You actually design one. In a cold pack, there's a little glass ampule in there, and you break it, and then the chemicals leave the glass ampule, which is a little weak piece of glass tubing that's been sealing each other, and then it gets cold. And there's, instead of potential energy, there are two things that make up energy. One is called potential energy. There's a fancy name for that, it's called enthalpy, but potential energy. And the other is entropy. And probably most of you have heard of entropy. And entropy is a measurement of randomness. So really, it's two of those together. So instead of potential energy, we can put G there, which combines both of those together. But for our class, it's potential energy. Not even the fancy name, just potential energy. Okay. All right, any questions about this at all? Kind of a qualitative look at reactions. Okay, so if you have a reaction, one of the things you need to do, unless you're in biochemistry or organic chemistry, you have to balance the equation. In those classes, they don't balance equations. So what is balancing the equations? Okay, balancing a chemical reaction or a chemical equation means one thing. What we start with, we have to end with, otherwise it's a big explosion. E is equal to mc squared. You can convert mass to energy. So the first step on balancing an equation is taking an inventory. What are the atoms? Well, okay, so this reaction, we have calcium chloride, sodium hydroxide, calcium hydroxide, and sodium chloride. So we have calcium, we have chloride, sodium, oxygen, and hydrogens. So those are the elements in that reaction. And they have to appear on both sides of the arrow also. Okay. You've got two numbers in chemical equations. You have coefficient out front, and you've got a subscript. Coefficients can change.
Subscripts cannot change. So we're balancing the reactant elements with the product elements. The only number we can change is the coefficient number out front. Now notice on this reaction here, there are no numbers. Okay, that means they're one. So you have the option of putting ones down or leaving them off. If you leave them off, just remember it's a one there. Now, this is like algebra. Okay, the coefficient works like that in terms of the numbers. So based on this, how many calciums do I have on the left side, on the reactant side? One. One times one is one. How many chlorides? Two. Okay, how many sodiums do I have? One. Same thing here now. One oxygen, one hydrogen. Okay? Everyone okay with those? I'm gonna do the same thing for the products. Okay, we have one calcium. So now the calciums are balanced. Okay, now notice the subscript down here, outside the parentheses. That means that 2 applies to both of those. So there's 2 OHs. So you can think of this as in your mind like that. Only in your mind, not on paper. Okay, so how many oxygens do we have on the right? 2. How many hydrogens? 2. Okay, over here on the far right, how many sodiums? And chlorides, 1. Okay, so after we do our inventory, these numbers don't match. We have to fix it so it does match. And we fix it by modifying the coefficients. Now, there's a fancy name for this process. It's called, I hate to say this, guess and check. So we're going to change it and we do the inventory again. So we keep doing guess and checks until the numbers match. Now, at first, if you've never done these before, it seems like kind of stupid. Like, why isn't there a better method than that? There is actually, but you have to have something called matrix algebra, and that class is available after you have the second semester of calculus. So how many of you have had 2 semesters of calculus? Gosh, no one's raising their hand. So we get to use guess and check. If you'd like to learn how to do that, I have a worksheet in files. You'd like to see how to do that. And you use your calculator because calculators are quicker than doing matrices by hand. Also, I have an extra credit equation to balance if you're interested in doing that, which is in files. I'll show you. Okay, so let's start changing some numbers here. We need some room here. So let's. All right. Now this is the guess part. We can choose any one of those coefficients to change. Doesn't matter. And then we do an inventory. Okay, so let's say we need 2 chlorines on the right because we only have 1. So if we change that, oops. To a 2, that's going to give us 2 chlorines and 2 sodiums. Now the chlorines match and the calciums match. The oxygen and hydrogens don't match. So what if we change this coefficient? Okay, that will change the numbers on the left. So that makes that 2 2 oxygens and 2 hydrogens. That's correct. Okay, so that's balanced. Why? Because the numbers on the left in the inventory equal the numbers on the right. Now, I've got tons of practice for you on this, by the way. Because if you've never done this before, you really need to practice it a lot. Some problems are really hard to balance, other ones are trivial. Okay, are there any questions about this? So, inventory, check. The inventory isn't correct. Change coefficients. Check. Each time you've got to do a new inventory. And sometimes when you change one thing, you change other things. Like when I change the over here. When I change the number of 1 to 2 to make the chlorines match, I also change the sodium at the same time. Okay, so any questions about that one? Okay, so we have, this is propane. This is oxygen gas. Okay. So this is what you do when you're barbecue outside. You have your tank of liquefied propane, and then you have an oxygen source, which is just like our Bunsen burners in the lab. We have a little opening so oxygen can get in. Those mix together, and we produce carbon dioxide and water and heat. So what kind of reaction is this? Is this endothermic or exothermic? Exothermic, because it's getting hot. Okay. Inventory. We have C, H's, and O's. Okay, we have 3 carbons on the left, 8 hydrogens, 2 oxygens, 1 carbon. Now, oxygens, we have 3 because we got some from carbon dioxide and some from the water. Together, we have 3. Then we have 2 hydrogens. So obviously, we don't have a match. So now it's coefficient guessing time. All right, so which one do you want to change? What do you think? Huh? All right, let's change the carbons. Okay, we got 3 carbons on the left, 1 on the right. So how can we make 3 carbons on the right? Huh? Okay, so we're going to change the 1 here. Remember, this is a 1. I'm going to change that to a 3. Now we have to take inventory because that's going to change the oxygens. Okay, so that makes that 3 carbons. And then we have 6 oxygens plus 1, it makes that 7. Okay, it's still not balanced. Hydrogens are a problem. What can we do to the hydrogens on the right? We do 4. 4 times 2 is 8. And then we have 4 more oxygens. So we have 6 here, 4 there, so that's 10 oxygens. Now everything matches except for those oxygens on the left. So what can we do to the O2
to make it 10.
5. 5 times 2 is 10. Now it's balanced. Now let's do, are any questions how I got those? I started on carbon because he said, let's start on carbon. We could have started on hydrogen. It wouldn't have mattered. We would still end up in the same place. Now, the purpose okay, why do we balance equations? There is a mole relationship of the coefficients. Here we go again with moles. Remember I said 99% of this class is going to be talking a lot about mole stuff, particularly when we talk about the quantitative side of things. And remember the word mole, what did it come from? It was the molecule. So there's a molecular relationship also. So there's not a mass relationship. However. Now, there is a mass relationship, but it's not between the coefficients. The mass relationship so collectively, all the mass of the reactants, when the reaction is done, equals the mass of the products. The coefficients don't come into play at all. So if you start with 10 grams of stuff, you're going to end with 10 grams of modified stuff, but it's still 10 grams. And that's 10 grams exactly. Is any difference? If there is a difference, that means there was a nuclear reaction going on where you're losing or gaining mass. That means we have flashing bursts of energy, also called the mushroom cloud here. All right, so make sure you know these relationships. Okay. Are there any questions about those relationships? Okay, so you don't need this twice. So let's. Actually, what did we just did? We just finished one with propane. Let's do it with butane. Same stuff that's in your lighters. Butane is 4 carbons in the fuel. So let's do an initial inventory. So we're going to have 4,
N, 2. 1, 3, 2. So all I did is here's the 4, here's the 10, here's the 2, here's the 1, the 2, and the 3. Okay, well, we started on carbon before. Let's just do carbon again. Okay, so we need 4 carbons on the right. So put a 4 here. That'll give us the 4 carbons. Got to redo inventory though. So we have 8 and 1 is 9. Everyone see where I got the 9? The sum of coming from carbon dioxide and water together. Okay. Hydrogens messed up. Okay, we got 10 on one side, 2 on the other. So we're going to put a 5 here. That'll make that 10. And that also affects our oxygens. So we have 8 oxygens, 5 is 13. So our oxygens are messed up. How do we get 13 oxygens from that O2? 2 times what is 13? 6.5. Six and a half times 2, 13. It's balanced. But there's a problem though. Is if we go back up here and look at number 2 here, the molecular relationship. Okay, let's go back up to the sky here. Okay, what this says from a molecular perspective, 1 C3H8 binds with 5 oxygen molecules, yielding 3 carbon dioxides and 4 water molecules. Okay, that's what the molecular relationship is. Let's look down here, the one we just did. This says we have 1 butane, that's the C4H10, and 6.5 oxygen gases. How can we have 6.5 molecules? Can't. So we have to fix that. How do you think we're going to fix it? If we were to add how do we do that fraction problem? When we were doing naming, we ran into this problem. Remember? We need a common what? Common denominator, which is what? 6. What about that one? What's the common denominator here? 4. And one of them is already in 4. So we're going to convert this to 2/4. And we can add them easily now. Okay, as far as this equation goes, the coefficients are in a ratio. Okay, just like we have one is to 2, it's 2 is to 4. The ratios are the same. Even though the numbers aren't the same, the ratios are the same. So what we're going to do now is we are going to fix the ratios. Just how I converted 1/2 to 2/4, we're going to convert the coefficients to get rid of that fraction. How do you think we're going to do that? Huh?
Yeah, and what do you think that would be? Well, if we can get rid of if we rewrite this instead of 6.5, let's write it as. (13/2). So how can we get rid of that 2 in the denominator? That 13/2, how can we get rid of that? If we multiply 13/2 by 2, what do we get? What does that equal? 13. So we multiply 13/2 by 2, we'll get our 13, whole number. But what we do to that one, we've got to do to everything else. So we multiply that one by 2. This is by 2. That's by 2. And that's by 2. As long as you multiply everything by the same number, it still stays balanced. But it's got to be balanced first. This doesn't work if it's not balanced first. It doesn't work at all. In fact. You can also divide everything by 2 if you want, as long as it's balanced. So now we have 8 carbons, 20 hydrogens, 13 oxygens. Over here we have 8 carbons, 16 and 10 is 26. 13 times 2 is 26. Okay, so this now becomes 13. We multiplied it by 2. So the lesson here is it's okay if you have a fraction. Just don't leave it. Fix it. And 99.9% of the time, it's by 2. Sometimes it's by 3, but most of the time it's by 2. All right, so what we've done is, let's practice. Okay, why don't you try doing these on your own? First step, inventory. And modify the coefficients. Take inventory again. And that's the process. Keep doing that, guess and check. Coefficient guess, and then you check inventory. Coefficient, change, inventory. So they balance.
Yes.
Now, on the second one, there's a trick I'm gonna show you in a minute. Make life a little bit easier. The first one's called rocket fuel, by the way. And the country, one of the alternatives to gasoline is they're talking about burning ammonia. And this is exactly the reaction that they use. Ammonia is easy to make. Make it from nitrogen in the air. It's called the Haber process. And it burns fine. I don't like the smell of ammonia personally. I had my farm, we used ammonia for fertilizer. We actually inject ammonia gas into the ground. And supposedly, it worked. It was kind of hard to believe at first. I'm going, well, anyway, it burns fine. So hold it.
Cars also burn methanol as fuel.
Yeah, there's a lot of stuff. Hydrogen. In fact, the state of California just got billion to improve its hydrogen alternatives for public vehicle. $1 billion in the government. You know, there's a big facility in West Sacramento for fuel cells right off the freeway. And all the major manufacturers, car manufacturers, have research facilities there. They're looking at fuel cells. So which use oxygen. So kind of cool. All right, so let's start balancing these things. Inventory first. So we're gonna go NHO. And you've got 1, 3, 2. 1, 2, 2. So we have a problem. Who was successful with this? What did you do first?
So, I wrote out, my inventory, and I don't remember the pilot, so marketing stuff, not right. I should just test all of that, this is my concept. And the progress is trying, like, I would change that, so I'm trying to find, very little factors, so I think I'll factor 3 and 2 is 6, that's a 2 in front of H, and that is 6. And then I
Put a 2 in front of here. Okay, wait a minute. So now what'd you put in front of the O2? You left it alone? Okay. Okay, and the NO? Okay, and the water? 3.
And then I found that because of what I did, I found that oxygen now is 3 on the side.
So it's 4, right? Okay, and
Yeah.
and the
And then I just 2 on the left side. Oh, right.
like that. Okay. Looks good. All right, is that the same numbers used?
That was my process. I got to different numbers, based on my guidance check, going back and forth. So eventually.
Well, if that's where you ended up, you're fine.
I ended with 15 ballots. I was saying that my process going back and forth.
Yeah.
I ended with 4 NH3 plus 5 O2, turns into 4 NO plus H2O.
So you didn't end with these numbers.
No, I was just saying that my process going back and forth
Okay.
to get.
Well, these numbers work. Except for one problem. What's the problem? Huh? Nitrogen, yeah. So what can we do? Well, we can put 2 nitrogens there. Okay, that makes that 2. And now we have 5 oxygens. So 2 times what is 5?
.5, or think of it as an improper fraction. So 5/2 times 2 is 5. This will make it easier to clear. So now we have 5 oxygens, so we're in good shape now. Right? 2, 2, 6, 6, 5, 5. Okay, we got to clear the fraction. So we're going to multiply everything by 2. So that becomes 4. That becomes 5, 4, 6. So all these numbers are double. So that becomes 4, 12, 10, 4, 12, 10. So go back to what the balance equation tells us. This says 4 molecules of NH3 react with 5 oxygens, which gives us 4 NOs and 6 waters. Secondly, gives us 4 moles, reacts with 5 moles of oxygen. Product gives us 4 moles of nitrous oxide, NO, 6 moles of water. So molecule and mole can be interchanged. And the reason why we can't leave the fractions as fraction is because it's a molecular relationship, and you can't have half the molecule, but I have whole molecule. Okay, everyone get those numbers?
Got 2, 2, 2, 3.
When you did your inventory, it matched.
Yeah. Again, 2 O2s, that's 4. 3 O2s at the very end, or 3 O's at the very end is 3 plus 1 is 4. Oh, duh. No, you can't.
Okay, so on the second one here. We have KNOHC. Inventory is going to be 1, 2, 1, 1, 6, 6, 2, 1, 1, 1. So potassiums don't match, hydrogens don't match. Okay, so we start fiddling with those. And this is going to require a fair amount of fiddling. Now, the other way to do it is we are going to group some of these. We're going to group it into ions. So we can think of this as nitrate. What does that sound like? Okay, so we've got nitrate on one side and nitrate on the other. So let's treat nitrates as nitrate rather than splitting it up. Now this only works, repeat, it only works if you have nitrate and a nitrate. It's going to be on both sides, the same ion form. So instead of K's, K's are okay because that's a K plus. K is fine. Then we're going to have an NO3. An H and a CO3. So we're just grouping them. But again, I want to emphasize, this works great as long as they're on both sides. If they're not on both sides, you've got to split it up. This will save you a ton of time if you can notice that. Okay, so how many nitrates we have on the left? 1. How many on the right? 1 again. How many H's on the left? 2. 1 on the right. We have 1 carbonate on the left, 1 on the right. Okay, so how can we fix the H's? Someone say 2. Okay. So that makes it H2. And it kicks the nitrates up to 2 also. Notice we have 2 potassiums, 2 Ks, 1 K on the left. So let's bump that up to 2. That gives us 2 Ks, 2 nitrates. All done. See how much quicker that was? They can do that the other way, where you take everything apart and you'll end up in the same place. It's just that it's more time. Now, the interesting thing here is you have oxygens here and oxygens here. But because they're tied up in an ion, they aren't the same oxygens. One is a nitrate oxygen, the other is a carbonate oxygen. They're not the same. But keep them separate. The other way to do this is just say, well, this is X. That's Y. Substitute in X and Y. And then at the very end, you substitute it back. Either way works. Now, if you get an equation like this, that's going to be a real pain to balance. But you look at the carbonate, excuse me, the ammonium NH4 ion, ammonium ion on both sides. We have a phosphate, PO4, PO4 on both sides. And we have nitrate both sides. So we can do this the same way. So instead of doing it like this, where we have the separate nitrogen, hydrogen, phosphorus, oxygen, and lead, we're going to do it as in NH4, PO4, lead, NO3. We're going to have 3 NH4s, 1 over here. 1 PO4, 4 PO4s over here. 1 lead, 3 leads, 4 nitrates, 1 nitrate. Everyone see where I got those numbers? So why don't you go ahead and try balancing this now using the group method.
Okay, let's do this. Now, this is a little challenging. Okay, so, let's just start with the leads. Okay, we got 3 leads on the right, 1 on the left. Let's make that 3. That kicks the nitrates up to what? Well, that's 3 times 4 is 12. Okay. So the nitrates on the right, put a 12 here. That gives us 12 nitrates and 12 NH4s. And we have, they come in 3s over here. So we need 12. So if we put a 4 here, 4 times 3 is 12. And that kicks the phosphates up to 4. We're done. Okay, does anyone need more time copying this?
I wanted to show you where the practice stuff is on Canvas before we stop. Then, okay. So we go to Canvas files. And if we look on Unit 3, periodic table, you'll see equation balancing, equation balancing, equation balancing, and here's the extra credit. Now that doesn't look very hard. The average person takes about 90 minutes. Just and don't be afraid of large coefficients. Okay. And you're going to do this, turn it in with your next test. Right. This will just go directly on your test. It'll be 5, 10 extra. No, you're gonna do it at home. And then bring it completed and you're gonna staple it back.
And we turn into the mirror here, just like that. Takes it, you know, the test day.
Well, you can show it to me, and I'll grade it, but then still include it though. On your test, because otherwise, I don't want you missing points. Okay, anyway, the name of it is called. Extra credit. Okay, then these others are just a whole bunch of. Number 9 here is the one we just did. And of course, I give you the answers. And one thing, forgot to show you. Say, a test. You balance this, only your answer was. Instead of 4, 3, 1, 12, you got 8, 6, 2, 24. That is still balanced. Still balanced. So when you're looking at my answers on the practice worksheets, if yours is a doubling of the answer, you're fine. Because when we get to next week, we get into the true stoichiometry. We're looking at ratios.
And because we're doing ratios, 1/2 is the same as 2/4. One is just double. So that's why if this is doubled, it works fine. So keep that in mind when you're looking at the answers. And on the test, I will not mark your balance equation wrong if it's double also. Because the purpose of balancing it is to get the ratio. And that's the end thing. And that'll be the middle step on your stoichiometry problem. Okay, so that's it for today. Unless you have another question. Yeah. Say again, louder. Yes. It'll be the week of November 17th. And then I'll have, and you'll take it in here. Speaking of, let's see. Today- What?
November 17th.
Yeah.
Okay. Yeah, not the quick name.
So Zoe, answer question. There's a dry lab 6 and a wet lab 7. So the dry lab 6 home. And we'll do the wet lab here.
Wet lab here needs right up, and then dry lab home.
Yeah.
It's the same one?
Yeah.
Okay, wet lab. It's you said 6?
Dry lab 6, yeah.
Dry lab 6, okay,
It's called chemical pool.
and then 7,
It's single replacement.
wet, okay. Oh, thank you,
That lab goes pretty fast, which is probably why I have them together.
okay. Oh, that's what you were saying earlier. Okay.
Because we have single replacement, double replacement reactions,
Mhm.
doubles red lives, and they go pretty fast. So they're really cool. Yeah. You're putting drops of stuff together and colors change and stuff. And it's cool.
Hopefully I don't break any pieces. I was.
No poking from the bottom.
Yeah. Thank you.
Sure.
Plans closed for, are we gonna have a?
Well, no, we're gonna have it eliminated.
Oh, also, it asks, what's the quantity that relates, the mass of water to the moles of water? It isn't Avogadro's number, is it? The mass to the moles? Cause can't you find